This video is on the effect of substituents on electrophilic aromatic substitution. The substituents on an aromatic ring will have varying effects. We will focus on benzene for now, but all of this applies for other aromatic rings too. As the benzene acts as a nucleophile in electrophilic aromatic substitution, anything that increases electron density on the ring will make it more nucleophilic, and therefore the reaction will proceed more rapidly. Anything that decreases the electron density on the ring will make it less nucleophilic. What do we mean by that? Well, let's take toluene. It has a methyl group as a substituent. We recall that methyl groups were electron donating when we discussed stabilities of carbocations. So in this case, it is also electron donating, all because of that hyperconjugation of carbon-hydrogen bonds towards the p orbitals. Either way, what it means is that as it's electron donating, the electron density on the ring of the toluene is higher, and therefore it will react faster than benzene in an electrophilic aromatic substitution. However, once we have a substituent on benzene, we end up with positions around the benzene ring. Remember those ortho, meta, para positions. Well, what position does substitution occur? Let's see. Let's look at this nitration of toluene. We'll notice that it is not an equal spread. It is 60% on the ortho positions, 3% on the meta position, and 37% on the para position. Why do we see this pattern? Well, the reaction favors the most resonance stabilized intermediates. If we draw the arenium ion intermediate, that would result upon the addition of the nitronium ion at the ortho, meta, and para position, and then draw the resonance structures of these arenium ions, we will notice that at the ortho position and the para position, we are able to put the positive charge on the substituted position, i.e. we get a tertiary carbocation. This is much more stable than the secondary carbocations, whilst with the meta substitution, we will only get secondary carbocations. Long story short, the ortho and para substitution resonance structures of the arenium intermediate are more stable, and therefore they are more likely to occur. We would say that the methyl substituent on toluene is ortho-para directing. So now you may be wondering, well, why is ortho favored over para? Well, there are two ortho positions and only one para position. So this comes down to statistics. You are going to end up with more ortho substitution than para substitution because it's more likely. Let's look at anisole. Anisole clearly has lone pairs on the oxygen that can be donated into the aromatic ring, meaning that this species is most certainly ortho-para directing. If we subject it to nitration conditions, we'll find out that we get 31% ortho substitution, 2% meta substitution, and 67% para substitution. Why is para favored in this case? Well, due to the steric hindrance of the methoxy group, i.e. that methyl group is kind of blocking the ortho positions, the para position is favored. An alternative way of looking at this is if we draw the resonance structures of the starting material where the oxygen is donating its electrons into the ring. You will notice that we get negative charge on the ortho position and the para position. So it would make sense that these are the positions that are acting as nucleophiles in the mechanism. This also applies to all electron donating substituents, so therefore the rule of thumb is if the substituent can donate a lone pair, it is always ortho-para directing. So what about nitrobenzene? If you have a nitro substituent, well, you may quickly think that, oh, nitrogen has a lone pair, therefore it's electron donating. But if you think about it a little longer, the nitro group actually has a nitrogen with a positive charge. This makes the nitro group electron-withdrawing. It pulls electrons away from the ring. It is deactivating, making electrophilic aromatic substitution really slow. If we were the nitrate, nitrobenzene, we will notice that at the ortho position we only get 6%, para position only 2%, but at meta position we get 92%. so the meta is favored. Does this all make sense? Well, let's look at the resonance structures of nitrobenzene. We will notice that the cation appears at the ortho position and the para position, meaning that the least likely positions to act as nucleophiles are the ortho position and the para position. On the other hand, if we already get that substitution anyway, the arenium ion that forms will resonate the positive charge next to the electron-withdrawing nitro group, putting a positive charge next to a positive charge. This is extremely unfavored, both for the ortho and para position. However, if we get substitution on the meta position, we cannot resonate the carbocation onto the carbon next to the nitro group. Therefore, there is no such positive-positive interaction that destabilizes it. So in other words, this is less destabilized. The only reason we get meta substitution is because ortho and para substitution are less favored. It's not that meta is favored, it is just less unfavored. So, long story short, electron donating groups direct ortho-para substitution. If it's bulky, it's more likely to be para. And if it's electron withdrawing, we get meta substitution because it is a less unfavored reaction. You have a go. What do you expect the major products to be of these reactions? You may pause now. And here are the answers. Here is a table of substituents and their rate effects and regiochemistry in electrophilic aromatic substitution. I highly recommend you either memorize this table, at least become very familiar with it. You will notice that the substituents with lone pairs available are all activating, whilst if there is something that is also removing those lone pairs from the system other than the aromatic ring, they will be less activating. Alkyl groups are able to hyperconjugate, whilst halogens are the special case. They seem to have lone pairs and therefore are ortho-para directing, but they slow down the reaction. They are deactivating in that sense. Why is this? Well, it's because even though they can donate via resonance those electrons, there's the inductive effect that withdraws electron density from the aromatic ring. This is why we get a deactivating effect in rate, but it is still ortho-para, because once it has to donate its electrons, it will. After that, we get deactivating compounds which involve carbonyls or just partially positive charges, all of which slow down the reaction because they pull electron density away from the aromatic ring and are meta-directing because they unfavor meta substitution less than they do ortho-para.